4 light-years. If you've spent any time at all reading about space, you've probably come across that number before, casually tossed out as the distance to our nearest stellar neighbor beyond the Sun. It sounds almost approachable, doesn't it? 4. A small, friendly number, the kind you could count on one hand. Tonight, we're going to find out exactly how badly that small, friendly number is lying to you. We're going to take the fastest machines humanity has ever built, real spacecraft, real speed records, and we're going to point them at that nearest star and simply ask, how long would it actually take to get there? The answer is going to stretch your sense of time in ways that are difficult to prepare for in advance. If you're winding down for the night, let us know in the comments where you're tuning in from, and feel free to subscribe if you're new here. Now, let's begin. Our destination tonight is a small, dim, unremarkable star called Proxima Centauri, part of the Alpha Centauri star system, sitting a little over 4.2 light-years from Earth. It's the closest star to our Sun that we know of, our nearest neighbor in an otherwise mostly empty galaxy. In astronomical terms, that makes it practically next door. Compared to the hundreds of billions of other stars scattered across the Milky Way, most of them tens of thousands of light-years away, Proxima Centauri might as well be sitting on our doorstep. But here's where the trouble starts, and it starts the moment you try converting that friendly-sounding number 4 into units your imagination can actually grip onto. A light-year isn't a measure of time, despite how it sounds. It's a measure of distance, specifically the distance light itself travels in a full year, moving at roughly 186,282 miles per second, or 299,792 kilometers per second, a topic we explored in close detail in an earlier documentary. 1 light-year works out to about 5.88 trillion miles, or 9.46 trillion kilometers. Multiply that by the 4.24 light-years separating us from Proxima Centauri, and the true distance comes out to roughly 24.9 trillion miles, or about 40 trillion kilometers. Numbers that large stop meaning anything the moment you hear them. Trillion is simply too big a word for most human brains to genuinely process. So instead of leaving that number sitting there abstractly, let's do something more honest. Let's take the actual fastest machines our species has ever built and find out, in real, concrete terms, how long the trip would genuinely take. Start with the current outright speed record holder, NASA's Parker Solar Probe. In December of 2024, diving in extraordinarily close to the Sun to study its outer atmosphere, Parker reached a top speed of about 690,000 kilometers per hour, or approximately 430,000 miles per hour, making it, at that moment, the fastest object human beings have ever built. To put that speed in perspective, at that pace, Parker Solar Probe could circle the entire Earth in under 3.5 minutes. It's a genuinely staggering achievement of engineering, roughly 3 times faster than the previous record holder. Even at that record-breaking speed, though, here's what a straight-line trip to Proxima Centauri would actually require. Assuming Parker Solar Probe could somehow maintain that peak velocity indefinitely, which it can't, since that speed only comes from diving close to the Sun's gravity and fades as it pulls away again. The journey to our nearest stellar neighbor would still take approximately 6,600 years. 6,600 years using the single fastest machine humanity has ever produced at its absolute peak performance, sustained the entire way, a condition that isn't even physically realistic. For comparison, 6,600 years ago, the wheel had only just been invented. It gets worse when we look at spacecraft actually designed for genuine, sustained, long-distance travel outward, rather than a brief high-speed dive past the Sun. Voyager 1, the spacecraft we explored in detail in an earlier documentary, the most distant human-made object currently in existence, cruises through interstellar space at a steady 17 kilometers per second, or about 38,000 miles per hour. It's an entirely reasonable, sustainable speed for a spacecraft that has now been flying continuously for nearly 50 years. At that pace, the same trip to Proxima Centauri would take approximately 75,000 years. 75,000 years ago, anatomically modern humans hadn't yet begun their major migrations out of Africa. The entire span of recorded human history, every civilization, every written word, every war and invention we typically study, would fit inside that number more than 10 times over, with room to spare. And even ordinary chemical rocket technology, the kind currently used to launch every crewed and uncrewed mission humanity has ever flown, fares no better. Using today's chemical propulsion, the realistic estimate for reaching Proxima Centauri comes out to somewhere around 70,000 years as well, roughly in the same devastating neighborhood as Voyager's cruising speed. 3 completely different approaches. A record-breaking solar probe, a sustained interstellar cruiser, and ordinary chemical rocketry. And every single one of them lands somewhere between 6,000 and 75,000 years just to cross the gap to our closest neighboring star. So here's the honest, uncomfortable truth sitting underneath tonight's title. 4 light-years sounds close specifically because astronomy usually deals in numbers so much larger that 4 feels almost cozy by comparison. But cozy is the wrong word entirely. Using every meaningful measure of speed humanity currently possesses, our fastest solar probe, our farthest travelled spacecraft, our best chemical rockets, reaching our nearest star would still take longer than the entire written history of human civilization, and in most cases, considerably longer than that. We haven't even gotten to the actual hard part yet, because everything we've calculated so far assumes a straightforward, if brutally slow, journey. It doesn't touch the deeper, more stubborn problem hiding underneath all of it. Why we can't simply build something faster in the first place, and what specifically stands in the way. That's the question waiting for us next. In Part 2, we'll look at the actual physics standing between us and a faster spacecraft, a stubborn mathematical wall called the rocket equation, and why simply adding more fuel turns out to make the entire problem worse, not better. For now, let this first number sit with you in the dark. The very nearest star in the entire universe, our closest possible neighbor among hundreds of billions of stars, would still take longer to reach using our best current technology than every empire, every civilization, and every century of recorded human history combined. We left off with a genuinely uncomfortable set of numbers: 6,000 years, 75,000 years. every serious calculation landing somewhere in that same brutal range. The obvious next question is the one most people ask instinctively. Why not just build something faster? Add a bigger engine, more fuel, more thrust. Tonight, we're going to find out why that instinct, reasonable as it sounds, runs directly into one of the most stubborn walls in all of aerospace engineering. The wall has a name. It's called the rocket equation, first properly derived by the Russian scientist Konstantin Tsiolkovsky back in 1903, decades before anyone had actually launched anything into space at all. And despite being over a century old, it remains essentially unchanged, one of the most fundamental limits governing every rocket humanity has ever built, or ever will build, using conventional propulsion. Here's the core problem the rocket equation describes in plain terms. A rocket doesn't just carry fuel the way a car carries gasoline, burning it, and leaving the weight behind gradually as a minor afterthought. A rocket has to carry the entire mass of that fuel with it, accelerating it right alongside the payload for as long as it remains unburned. And to accelerate a heavier rocket, you need more fuel. But that additional fuel itself has mass, which means accelerating it also requires more fuel still, which itself has mass requiring yet more fuel to move. This isn't a minor inefficiency. It's a runaway compounding relationship, where the fuel required to achieve a given change in velocity grows not steadily, but exponentially, as that desired velocity increases. To make this concrete, engineers use a measurement called delta V, essentially the total change in velocity a spacecraft needs to achieve across its entire mission. Getting a spacecraft from Earth's surface into low orbit requires roughly 9.4 kilometers per second of delta V, about 5.8 miles per second. An already formidable engineering challenge, one that consumes the overwhelming majority of a rocket's total launch mass in fuel alone. A typical rocket sitting on the launch pad is around 90% fuel by weight, with the actual payload, the part that does anything useful, making up only a small fraction of the total. Now stretch that same relationship out toward the kind of speeds we discussed in Part 1, speeds anywhere close to a meaningful fraction of light speed. The delta V required isn't just larger, it's larger by a scale that breaks the exponential relationship entirely. Using the rocket equation with any chemical propellant available today, reaching even 10% of light speed, a speed that would still take over 40 years to reach Proxima Centauri, would require a fuel-to-payload mass ratio so extreme that the numbers stop being physically buildable. We're not talking about needing a bigger rocket. We're talking about needing a rocket whose fuel mass would, in the most extreme calculations, exceed the mass of entire planets, just to carry a payload the size of a small spacecraft up to that speed, using chemical combustion as the method of propulsion. This is precisely why every realistic estimate we discussed in Part 1 landed in the tens of thousands of years, rather than anything faster. It isn't a failure of ambition, or funding, or willpower. It's a mathematical ceiling built directly into the physics of chemical combustion itself. Chemical rockets work by burning fuel and expelling the resulting exhaust at high speed out the back, and the exhaust velocity of even our best chemical propellants tops out at only a handful of kilometers per second. No matter how the fuel is arranged, no matter how efficiently it's burned, that exhaust velocity puts a hard, unmovable ceiling on how much speed a purely chemical rocket can ever realistically deliver, regardless of how much fuel you're willing to carry. Engineers have understood this limitation for decades, and it's exactly why serious proposals for interstellar travel abandon chemical propulsion almost immediately, in favor of something with a fundamentally higher exhaust velocity, a fundamentally different relationship between fuel and thrust. This is where ideas considerably stranger than ordinary rockets start entering the conversation. Nuclear propulsion, where instead of burning chemical fuel, a spacecraft harnesses nuclear reactions, either fission or fusion, to achieve exhaust velocities many times higher than any chemical engine could ever produce. Ion propulsion, where a spacecraft accelerates charged particles using electric fields rather than combustion, achieving remarkably high exhaust velocities, though only ever producing a tiny, gentle amount of thrust at any given moment. A thrust so gentle it would take months just to accelerate a probe up to highway speeds, but one that can, patiently, keep pushing for years at a stretch, gradually building towards speeds chemical rockets could never sustain. And more exotic ideas still, involving no onboard fuel at all, instead relying on external power sources entirely. One of the most genuinely serious of these exotic proposals involves abandoning onboard propellant altogether and pushing a spacecraft using something external instead: light itself. If you mount an extremely thin, extremely lightweight reflective sail onto a small enough probe and shine a sufficiently powerful, tightly focused beam of light at it, from a laser array here on Earth or in Earth orbit, the light itself, through the physical momentum it carries, can push that sail forward without the spacecraft needing to carry any propellant mass at all, remove the fuel entirely from the equation, and the exponential problem we've spent this entire segment describing simply disappears. There's no fuel mass to accelerate alongside the payload, because there's no fuel on board in the first place. This idea isn't purely theoretical anymore. It's the basis of a real, currently active research program, one with a stated goal considerably more ambitious than anything we've discussed so far tonight. A program aiming not for tens of thousands of years, but for a genuinely staggering fraction of that time, using technology that, while not yet fully built, isn't science fiction either. That's exactly where we're headed next. In Part 3, we'll look closely at that program and at the broader landscape of serious, real proposals scientists have put forward for actually reaching another star, from nuclear-powered spacecraft first seriously studied back in the 1950s, to laser-propelled sails no larger than a postage stamp. And we'll be honest about exactly how far even the most optimistic of these ideas can realistically take us. Sit with this for a moment before we continue. Every rocket humanity has ever launched, every mission, every record-breaking probe has been fighting the exact same exponential wall the whole time. A wall built not from a lack of imagination, but from the simple, unforgiving chemistry of what fuel actually weighs. We left off with fuel as the enemy, chemical propulsion trapped by its own exponential mathematics, and light itself emerging as one possible way around the entire problem. Tonight, we're going to look at the actual, real, seriously studied proposals scientists have put forward over the decades to break past that wall, starting with one of the strangest and most genuinely audacious ideas ever taken seriously by a national government: propelling a spacecraft using atomic bombs. In 1958, in the tense competitive years following the Soviet Union's launch of Sputnik, the United States government's newly formed Advanced Research Projects Agency began funding a real, working engineering effort called Project Orion. The concept, first proposed by physicist Stanislaw Ulam back in 1947 and developed in earnest by physicist Freeman Dyson and bomb designer Ted Taylor, was almost absurdly direct. Eject small nuclear explosives behind a spacecraft, one at a time, and detonate them at a safe distance. Each explosion would vaporize a disk of propellant material, and the resulting blast of superheated plasma would slam into a massive pusher plate mounted on the back of the ship, shoving it forward. Then repeat, again and again, dozens or even hundreds of times, each individual nuclear blast adding a fresh increment of speed, absorbed and smoothed out by a sophisticated shock-absorbing system between the plate and the crew. It sounds almost like science fiction, but it wasn't. The team actually built and successfully flew a small-scale test model in November of 1959 using conventional chemical explosives rather than nuclear ones, achieving a controlled flight lasting 23 seconds and reaching a height of about 184 feet. Freeman Dyson calculated that a full-scale Orion craft, built as originally envisioned, could achieve genuinely staggering performance, capable of carrying vast payloads, hundreds of tons at a time, to Mars and back, within a matter of months, rather than the years required by conventional chemical rockets. Dyson didn't stop at planetary travel. As what he himself described as something of a lark toward the end of the project, he sketched out a theoretical interstellar version, sometimes called Super Orion, using far larger, more powerful thermonuclear pulse units instead of the smaller fission bombs used in the original design. His calculations suggested such a vessel might reach speeds up to around 12% of light speed, fast enough that the trip to Alpha Centauri, while still measured in decades rather than years, would genuinely be survivable within a single extended human lifetime, or as Dyson himself put it at the time, achievable within the lifetime of the grandchildren of the people working on the project. Project Orion never flew. The same nuclear detonations that gave it such extraordinary performance also made it politically and environmentally impossible to pursue. Freeman Dyson himself later calculated that launching a full-scale Orion from Earth's surface using the atmospheric nuclear testing methods available at the time would statistically cause a small but real number of fatal cancers from the resulting fallout, a consequence he considered morally disqualifying. The 1963 Partial Nuclear Test Ban Treaty, prohibiting nuclear explosions in the atmosphere, in space, or underwater, effectively ended any realistic possibility of testing the concept at all, and the project was formally cancelled in 1964 after 7 years of genuinely serious engineering work. The idea didn't disappear entirely, though. Between 1973 and 1978, a team of scientists and engineers at the British Interplanetary Society, led by engineer Alan Bond, revisited the underlying concept in a study called Project Daedalus, this time replacing Orion's nuclear fission bombs with a different, more advanced approach: inertial confinement fusion. tiny pellets of fusion fuel imploded and ignited in rapid succession by a different triggering mechanism rather than actual nuclear weapons. Project Daedalus was specifically designed as an uncrewed probe, aiming to reach a nearby star within about 50 years. A genuinely serious engineering study that, while never built, demonstrated that a fusion-powered interstellar probe was at least theoretically consistent with known physics, if not with any technology humanity had actually developed yet. Which brings us to the most current, actively funded, serious proposal for interstellar travel, one we touched on briefly at the end of Part 2. In 2016, physicist Yuri Milner, alongside the late physicist Stephen Hawking and Facebook founder Mark Zuckerberg, announced the launch of Breakthrough Starshot, a research initiative aiming to develop exactly the kind of light-propelled sail concept we described earlier. The plan involves building an enormous, powerful array of ground-based lasers capable of focusing a beam onto a fleet of tiny, wafer-thin probes, each one attached to an ultra-lightweight reflective sail only a few meters across, weighing, including all its electronics, only a few grams total. The stated goal is genuinely audacious: accelerating these tiny probes up to roughly 20% of the speed of light within a matter of minutes, using the sustained push of the laser array, then letting the probes coast the rest of the way to the Alpha Centauri system entirely under their own momentum. At 20% of light speed, the journey to Proxima Centauri would take a little over 20 years, a genuinely staggering improvement over every number we discussed back in Part 1. Compare that to the 6,600 years required at Parker Solar Probe's record speed, and you begin to appreciate just how large a leap this proposal represents, a jump of more than 300 times in velocity, made possible specifically by discarding onboard fuel entirely and relying on an external power source instead. It's important to be honest about exactly where this project actually stands today. Breakthrough Starshot remains a research program, not a mission with a scheduled launch date. Building a laser array powerful enough to achieve this kind of acceleration requires engineering that doesn't yet exist at the necessary scale, sails that can survive extreme heating and acceleration without tearing apart, electronics miniaturized down to the size of a computer chip while still carrying cameras, sensors, and a working communication system, and a method of aiming that kind of precision across interstellar distances with enough accuracy to actually reach the target system at all. And even in a fully successful scenario, the probes themselves would only ever achieve a brief, high-speed flyby of the Alpha Centauri system, unable to slow down or enter orbit, gathering what data they can in the fleeting moments of closest approach before continuing on, indefinitely, into the emptiness beyond. So here's where tonight's search for a faster path to the stars actually leaves us. From atomic bombs strapped to a massive steel pusher plate, to fusion pellets imploded in careful sequence, to a fleet of postage stamp-sized probes riding a beam of laser light, every serious proposal humanity has put forward shares the same underlying lesson we uncovered in Part 2. The moment you abandon conventional chemical fuel in favor of nuclear energy, or fusion, or external propulsion using light itself, the numbers improve dramatically, sometimes by factors of hundreds. And yet, even in the most optimistic best-case scenario currently being seriously researched, reaching our very nearest star still requires decades, using probes so small they could never carry a human being at all. Which raises the obvious, harder question waiting for us next. If even the best proposed technology can only manage a fast, unmanned flyby, taking 20 years at an absolute best-case minimum, what would it actually take to send people, not just probes, across that same distance? What does a multi-decade journey through the radiation and emptiness of interstellar space actually do to a human body and to a human mind? And is a crewed mission to even our closest neighbouring star realistically possible with anything resembling foreseeable technology? That's the question we'll sit with next. In Part 4, we'll look honestly at the human cost of a journey like this, the radiation exposure, the sheer duration, and the genuine engineering limits standing between a clever probe design and an actual, livable, crewed spacecraft. Here's something worth holding on to as you drift towards sleep tonight. 67 years ago, a small team of physicists in Southern California seriously believed they could ride a chain of atomic explosions all the way to another star, and they were not entirely wrong. We left off with an honest limitation. Even the most promising currently funded interstellar concept, Breakthrough Starshot's laser-driven sails, is designed exclusively for tiny unmanned probes, weighing only a few grams, incapable of carrying a human passenger of any kind. Tonight, we're going to ask the harder, more uncomfortable question directly. What would actually happen to an actual human being attempting to survive a journey of this length and distance? And why even our most advanced current thinking runs into a wall long before the engineering problems are even fully solved. Let's start with the danger hiding in plain sight the moment any spacecraft leaves the protective bubble surrounding Earth. Our planet is shielded in two overlapping ways from the majority of the dangerous high-energy radiation constantly drifting through space. Earth's magnetic field deflects much of it, and our thick atmosphere absorbs most of what gets through regardless. The moment a spacecraft leaves both of those protections behind, the radiation environment changes dramatically, and not in a small, easily managed way. We actually have real, measured data on exactly how much worse it gets, thanks to instruments carried aboard NASA's Curiosity rover during its 8-month journey to Mars. While cruising through open interstellar adjacent space, unprotected by any planetary magnetic field, the rover's radiation detector recorded an average dose of about 1.84 millisieverts per day. To put that in a frame of reference actual radiologists use, that's roughly equivalent to receiving a chest X-rays worth of radiation exposure every single day, for the entire duration of the trip. A full round-trip mission to Mars, factoring in the outbound cruise, time spent on the surface, and the return journey, was estimated to expose astronauts to a cumulative dose of just over 1 full sievert of radiation, an amount associated with a measurable, real increase in lifetime cancer risk. For comparison, NASA's official career radiation limit for astronauts currently sits at 600 millisieverts, which means a single round-trip Mars mission alone, using a journey lasting less than 3 years total, would already push an astronaut close to or past their entire career radiation allowance. Now hold that number up against the timelines we've spent this entire documentary establishing. A Mars mission, at its longest, might last around 3 years total. Even Breakthrough Starshot's extraordinarily optimistic 20-year, laser-propelled flyby concept, the fastest realistic proposal we've discussed all night, is designed exclusively for tiny, unmanned, disposable probes, precisely because no human being could survive that duration of unshielded radiation exposure using any radiation protection technology that currently exists. Extend the timeline further, out toward the 60 to 75,000 years required by Voyager speed or chemical rocket travel, numbers we established back in Part 1, and the entire concept of radiation exposure limits stops being a meaningful engineering constraint at all. No shielding technology, however advanced, changes the fact that a multi-thousand-year journey would require multiple complete human generations living, aging, and dying aboard the vessel. An entirely different category of engineering and social challenge that we've actually explored in close detail in an earlier documentary about generation ships, examining exactly what it would take to keep a small, closed population of humans genetically healthy, psychologically stable, and culturally intact across centuries of total isolation. Radiation is far from the only physical obstacle standing between current technology and a genuinely survivable human journey to even our nearest star. Extended time in microgravity, the kind experienced during any long-duration spaceflight, causes measurable, well-documented bone density loss and muscle atrophy, effects that have been carefully studied and partially mitigated aboard the International Space Station through rigorous daily exercise regimens, but never for anything close to the multi-year timescales a genuine interstellar mission, even at Breakthrough Starshot's optimistic speeds, would actually require. Any realistic crewed design would likely need some form of artificial gravity, generated through continuous rotation or acceleration, an entire additional layer of engineering complexity that adds significant mass, and therefore, circling back to the exact exponential fuel problem we explored in Part 2, significant additional propulsion requirements as well. There's also the matter of life support itself, needing to function flawlessly, without failure, for however many years or decades the mission actually requires, recycling air, water, and waste in a fully closed loop, with no possibility of resupply from Earth at any point along the way. We've already seen in our documentary examining the real-world Biosphere 2 experiment just how difficult it proved to maintain a stable, balanced closed ecosystem even for 2 years, inside a structure built specifically for that purpose, sitting safely on Earth's own surface with a full team of scientists monitoring every variable. Scaling that same challenge up to a genuine, uninterrupted, multi-decade interstellar voyage, with failure meaning the complete loss of the entire crew, represents an engineering challenge of a fundamentally different order of magnitude. Taken together, radiation exposure alone effectively rules out any currently foreseeable crewed mission lasting more than a handful of years using existing shielding technology. The fastest proposed method of interstellar travel, Breakthrough Starshot's laser-propelled sails, deliberately sidesteps this problem entirely by never attempting to carry a human being in the first place. Every other approach we've discussed tonight, Project Orion's nuclear pulses, Project Daedalus's fusion drive, ordinary chemical propulsion, would require a journey measured in decades at the very best, and tens of thousands of years at the more realistic, achievable end. A timescale that pushes the entire challenge from spacecraft engineering into something closer to civilizational engineering instead. So here's the honest, complete picture. Once every piece we've gathered tonight is finally placed side by side. Reaching our nearest star with an unmanned probe, using technology actively being researched right now, might genuinely be possible within a couple of decades, assuming several significant remaining engineering breakthroughs actually materialize. Reaching that same star with an actual living human being arriving alive, healthy, and capable of doing anything meaningful once there, remains, using any technology currently on the horizon, somewhere between extraordinarily difficult and functionally impossible, not because of a single insurmountable problem, but because of the same pattern we've traced through this entire documentary. Every solution to one obstacle immediately runs headlong into another, equally stubborn constraint waiting directly behind it. In our final part tonight, we'll step back from the specific engineering challenges entirely and put the full picture in its proper, humbling context. Because for everything we've discussed, every staggering number, every decades-long best-case scenario, Proxima Centauri remains, by an enormous margin, the single closest star in the entire universe. And that raises one last, quietly unsettling question worth sitting with before we close out tonight's journey. If reaching even our nearest neighbor is this difficult, what does that actually tell us about everything else out there, scattered across the rest of our galaxy and the countless other galaxies beyond it? A small footnote worth carrying with you into sleep tonight. Every single astronaut who has ever traveled to the International Space Station has already absorbed more radiation in just 6 months than the total lifetime limit most nations set for ordinary workers on Earth. We've spent this entire night with a single star, Proxima Centauri, turning its deceptively small number, 4.2 light-years, over and over, examining it from every possible angle. Tonight, in this final part, we're going to step back and place that number inside the true, staggering scale of everything surrounding it, and discover that our nearest star, for all the difficulty it's already given us tonight, is really only the very first, smallest step of a staircase that extends almost beyond comprehension. Let's start by simply looking at what else is nearby, once you've accepted that Proxima Centauri is technically achievable, at least for an unmanned probe within a human lifetime. The next star system after Alpha Centauri, a red dwarf called Barnard's star, sits about 5.96 light-years away, already meaningfully farther than the target we've spent this entire documentary struggling to reach. Sirius, the brightest star visible from Earth, sits at 8.6 light-years. Widen that circle out to include every star within roughly 20 light-years of Earth, and you capture only a small handful of stellar neighbors, a few dozen scattered points of light, most of them faint, unremarkable red dwarfs, entirely invisible to the naked eye. Now widen the circle much, much further. Our entire Milky Way galaxy, home to somewhere between 100 and 400 billion stars, measures roughly 100,000 light-years across. The distance from our solar system to the galaxy's own center, where a supermassive black hole named Sagittarius A star quietly anchors the entire structure, is approximately 26,000 light-years, more than 6,000 times farther than the trip to Proxima Centauri, that is already, across this entire documentary, proven to be at the very edge of achievable technology. At Voyager's cruising speed, the 17 kilometers per second we discussed back in Part 1, reaching the center of our own galaxy wouldn't take 75,000 years. It would take something in the neighborhood of 450 million years, a span of time stretching back before the first complex animal life had even crawled onto land here on Earth. And the Milky Way, despite containing hundreds of billions of stars, is itself only one galaxy among an almost incomprehensible number of others. The Andromeda Galaxy, our nearest large galactic neighbor, which we discussed in our earlier documentary on the true speed of light, sits approximately 2.5 million light-years away, a distance so vast that comparing it to the trip we've spent tonight struggling with feels almost absurd, roughly 600,000 times farther than Proxima Centauri. And Andromeda itself is, on a cosmic scale, practically next door. The full observable universe, as we discussed in that same documentary, stretches across roughly 93 billion light-years, containing an estimated 2 trillion galaxies, each one holding hundreds of billions of stars of its own. Sit with that comparison for a moment, because it genuinely reframes everything we've spent this entire night working through. Every staggering number from tonight's journey, the 75,000 years at Voyager's cruising speed, the 6,600 years using our fastest recorded spacecraft, even Breakthrough Starshot's genuinely optimistic 20-year best-case scenario, describes only the very first, smallest possible step outward from Earth. Proxima Centauri isn't simply hard to reach, it's the easiest star in the entire universe to reach, by an enormous, overwhelming margin, and it's already sitting firmly at, or slightly beyond, the outer limits of what current and near-future technology can seriously attempt. This is, in its own way, exactly what tonight's title promised from the very beginning. The distance to the nearest star really is worse than most people think, not because the number 4.2 is inaccurate, but because that small, friendly-sounding number quietly conceals just how enormous a light-year actually is, and just how far behind our fastest, most advanced engineering still lags behind the raw scale of even our closest possible cosmic neighbor. But there's something worth holding on to here too, something that isn't simply humbling, but also, in its own quiet way, genuinely remarkable. A little over 300 years ago, Ola Rimmer, a single astronomer with a telescope, first proved that light itself takes real time to travel at all. A little over a century ago, Einstein worked out why nothing could ever exceed that speed. Less than 70 years ago, a small team of physicists seriously calculated how a chain of atomic explosions might carry human beings toward another star within their own grandchildren's lifetimes. And right now, tonight, an active, funded research program is genuinely working to accelerate a fleet of postage stamp-sized probes up to 20% of light speed, aiming them directly at the very star we've spent this entire night discussing. We are, by any honest measure, nowhere close to actually crossing that gap yet, but we've gone, in a remarkably short span of human history, from believing light was instantaneous to precisely calculating exactly how slow and how difficult the fastest thing in the universe still makes even our nearest cosmic neighbor. That's not nothing. It might, in fact, be the single most important first step of all. Thank you for staying with us for this entire journey tonight, from the very first minute all the way through to the end. We put a lot of care into getting the science right and into telling it in a way that's actually worth your time, so it means a lot that you stuck around. If you enjoyed this one, subscribing genuinely helps, and it means you won't miss whatever we cover next. Good night and rest well.